Okay, so now that we know all about arrays and pointers and the relationship between them, we're going to look next at structs, or structures, which are useful collections of data in and of themselves, and also provide the foundation for classes, that is, object-oriented development using C++. So an array, as we've seen, holds elements that have the same data type. We can access individual elements within the array using the square bracket notation with an integer subscript. A structure is also like an array in that it contains many items. In the case of a structure, these are referred to as members, and these may have different types from each other, unlike the array where all the items have to be the same. The way we access a particular item or a particular member of a structure is by member name. That is, we use the dot followed by the member name after the name of the structure object. So here is an illustration. This is a structure definition for complex numbers. We say struct complex. So complex is a data type that we're defining here, basically. And what we're saying is that each complex structure has two components, two members. The first is called real, and its data type is double. The second is called imag, and its data type is also double. So in this instance, we have an example of a structure where the data types of the two members are the same, but that's not obviously a requirement. You do have to have a semicolon at the bottom of your structure definition. The structure definition does not allocate any storage. It does not create an object. What it does is to define a data type or a pattern that we can use to create individual objects. In main, what we're doing here is we're using this data type that we've just defined to declare an object C whose data type is complex. All right, so C occupies memory. In particular, it occupies enough memory to contain two doubles. The first of those doubles is named real. The second of those doubles is named imag. And we can access those members with the dot notation. Initially, this complex object is uninitialized. So it just contains garbage for both the real part and the imaginary part. If we say c.real gets 2.2 and c.imag gets -1.3, we now have some valid information, some valid data in this object C. We can initialize a structure using curly brace notation. This declaration and initialization says that C2 is a complex object whose real part is 7.0 and imag part is 3.3. The values are used sequentially in the order in which the components, the members, are defined. So real is 7.0 and imag is 3.3. Complex is a genuine data type, and so we get a ton of things for free having defined this complex structure. We can create individual complex variables, as we've done with C and C2 on slide 3. We also can create arrays of complex objects. We can create arrays of arrays. We can create pointers to complex objects. We even get assignment for free, because what will happen if I were to say something in slide 3 here like C gets C2, is that the real part of C2 would get stored into C's real part, and the imag part of C2 would get stored into the imag part of C. We also get the ability to pass values into functions as arguments, and also to return complex objects by value. So all of that behavior requires no additional work on our part. Now, if we want complex objects to behave like real complex numbers, we're going to have to provide a bunch of other higher level capabilities. We're going to have functions for multiplying two complex numbers together, adding one complex number to another. We're also going to want to be able to display a complex number, and on and on. So we do have a lot of work to do, even though we do get a lot of things for free. Let's take a look at some functions that we can define. Here we have a multiplication function. This function takes two complex objects as arguments. These are received by value, that is, copies of the values of these arguments get passed in and become the values of these two parameters a and b. We are declaring within the body of this mult function an object called prod, and we're using an arithmetic expression to compute the initial value for the real part of prod. So prod.real gets, or is initialized with, a.real times b.real minus a.imag times b.imag. And then the imaginary part is initialized with this other expression, again involving components of the argument parameters a and b. Once we have created an initialized prod, we can return a copy of prod as the result of this function, and then you'll see that the return type for mult is complex. Here we also have a simple little function that just displays a complex number. It returns void, okay, so it doesn't return anything. And if it's passed a complex object as its parameter, then the representation that it will display to see out is an open parenthesis character followed by the real part, followed by a comma character and the imaginary part, and then a closing parenthesis. Now, I said open parenthesis and comma characters. Actually, they're being represented here as string literals. I could have just as well used character literals instead, since these are just one character. Notice that, and this is a style point here, notice that we did not automatically display a new line character as part of putz, because we don't know when we develop putz that every time somebody calls the putz function, they're automatically going to want to have a new line character at the end. So we will leave it up to the person who calls putz to decide for themselves whether they also want to send a new line character to see out after that complex value has been displayed. Okay, so here we have a main function that's creating and manipulating some complex objects, an array of complex, and a pointer to complex. Let's have a look at what's going on here. And I want to put up some diagrams of what's going on when this program runs. Okay, so here on slide 8 is a memory diagram showing that the object z1 is created in memory. It's a local automatic variable, so it's created on the stack. It's not initialized, so the real and imag parts for z1 exist. Each of them is an 8-byte double, but they're uninitialized, so they just contain garbage. z2 here is also a complex object. It has been initialized. Notice that we're using the equal sign, the older style of initialization here, with the curly braces. So the real part is 1.1, and the imag part is 2.0. And then for z3, our third complex object in this program, we're using the more modern C++11 style of initialization without the equal sign. All right, so real is 5.7 and imag is 6.1. Next, we have ZA being declared and initialized. ZA is an array of 5 complex. It turns out, and this was described in a previous homework exercise, that if you give any initial value for an array, but not all of the initial values for all of the elements, then by default, all of the trailing elements are filled in with zeros. So we're using that knowledge here to just declare 0.0 as the value for the real part of the first element of the ZA array. All right, if you only give one value, that value gets used as the value of the first part of the first element of the array, and then all the other ones get filled in with zeros automatically. After ZA has been created and initialized, PZ is being declared here as a pointer to a complex object, and we're initializing PZ with the address of ZA sub 3. Okay, so ZA sub 0 is the first complex object in ZA, ZA sub 1, ZA sub 2, so ZA sub 3 is that complex object, and PZ is being initialized with the address of that object. Finally, in terms of declaring and initializing objects here, we have an object called zprod, and it's being initialized with the result of a call of our mult function. I'm not sure I've specifically said this aloud, but initializations can involve complex expressions involving arithmetic and logical comparisons and function calls and so on. So a copy of Z2 gets passed down into mult, and a copy of PZ sub minus 2 gets passed down as the second argument to mult. We can use negative subscripts in arrays, and we can use a pointer as though it were an array. So PZ is pointing here. PZ sub minus 1 is this complex prior to PZ, and PZ sub minus 2 is this complex here, equivalent to ZA sub 1. Now, I was not stupid in selecting PZ sub minus 2. It has both real and imaginary parts of 0. Therefore, that complex value of 0, 0 multiplied by anything is going to give me a 0. So I can conveniently fill in a 0 and a 0 for the real and imaginary parts of zprod. All right, so that's what's shown here. We're getting, as arguments to the mult function, we're passing in a copy of Z2 as the first argument, and a copy of PZ sub minus 2 as the second argument, and that's conveniently computing the product of 0, which becomes the initial value for zprod. Now, when I do this assignment, ZA sub 2 gets Z1, that's going to modify ZA sub 2, the third element of this array of 5 complex. The value put in there are going to be the real and imaginary values from Z1. Those are garbage, but that's fine. We'll just assign garbage from Z1 into ZA sub 2. Okay? So that works. ZA sub 0 gets Z2 is going to take the values of the real and imag parts of Z2 and copy those into the corresponding real and imag parts of ZA sub 0. All right, so that happens. And then finally, when I say star PZ gets Z3, well, PZ is pointing at this complex object, equivalent to ZA sub 3. And so star PZ gets Z3 is going to copy the 5.7 into the real part and the 6.1 into the imag part, so that we now have this situation. All right, so that's where we are at the bottom of the code on slide 7. Now this main function is going to continue a couple of slides down. Before we get to the remainder of this main function, we do need to talk some more about notation involving structures and pointers to structures. Now, if you have a particular object S that's a structure type with a particular member mem, then as we've already discussed, you can access that mem member by saying s.mem. But if you have a pointer to a struct, p, we know then that star p is the struct. The question is, how do we use the dot to access that particular member of this struct star p? Well, it turns out that the star has lower precedence than the dot. So what we need to do is to put the star p part in parentheses and then put the dot mem afterward. All right? So p is pointing to a struct, star p is the struct, and star p in parentheses dot mem is therefore the member of that particular struct. Many people forget the parentheses and write code that looks like this, but this fails because this is star of p.mem, and p.mem is trying to access the mem member of a pointer. Now, a pointer doesn't have any members. A pointer only contains an address of something. So p.mem is an error, and the compiler will yell at you if you do this. You've got to remember to use the parentheses around the star p if you want to use the dot mem to access the member of the pointed to structure. Furthermore, there is an alternative notation you can use instead. Everybody agrees that having to remember to put star p in parentheses and then following that with dot mem is nasty. It's hard to type. It's ugly to read, especially if you have nested pointers to structures containing pointers to other structures and so on. So rather than using the star in parentheses followed by the dot, you can use the arrow instead. Now the arrow is simply the dash symbol followed by the greater than sign. And this is a little bit like what we talked about for the relationship between pointers and arrays. It is always, always, always true that if p is pointing at some structure and that structure has a member named mem, then star of p in parentheses dot mem can be replaced with p arrow mem. They're exactly equivalent notations to each other. And so that gets us to the bottom of the main function with some examples of these notations. Okay, so on slide 11, we have the bottom part of this main function. Z2 is simply a complex object, and we can therefore directly access its real part by saying z2.real. Likewise, Z1 is a complex object, and we can directly access its imag part by saying z1.imag. Now, z2.real is going to be 1.1, which is, a valid value. Z1 is not initialized, so z1.imag is going to display some kind of garbage. ZA is my array of complex values. We did make some changes within ZA, so let's just recall our diagram. Actually, I'm going to move the code for slide 11 over to the left so we can recall our diagram. All right, so on this diagram is what's going on in memory with the objects Z1, Z2, Z3, and Zprod, as well as the array of complex objects ZA and the pointer to complex PZ. So Z2.real is 1.1. Z1.imag is this garbage right here. ZA sub 4.real. ZA sub 4 is the last item in this array, and its real value is 0. Upon display, we just get a 0 because remember, when you display a floating point, trailing zeros are not displayed, so the 0.0 part is not displayed by default. Now, PZ is pointing at this complex object. That is, it's the same thing as ZA sub 3. And therefore, if I say star of PZ in parentheses dot imag, that's getting me the imag part, whose value is 6.1. Equivalently, I can say PZ arrow imag. The arrow is exactly equivalent to using the star in parentheses and then the dot. I can change PZ arrow imag to minus 2.7. Okay, so that's going to do this. what used to be a 6.1 is now a 2.7, pardon me, minus 2.7. ZA sub 1 dot real, well, let's see, ZA sub 1 is this complex object, and ZA sub 1 dot real is the real part. So the real part of ZA sub 1 is going to get 9.6 from that next assignment. All right, so now we have a 9.6 there. ZA, well, let's think about this. ZA is an array of complex. Recall that ZA is equivalent to the address of ZA sub 0. So I can think of ZA as pointing directly at this first complex object, and I can therefore use the arrow notation to say ZA arrow real gets minus 3.1. So that's going to put a minus 3.1 in the real part of the first element of ZA. Okay. So we've illustrated the star and the dot, we've illustrated the arrow, we've illustrated the dot notation for accessing members of complex objects. Now we're calling putZ, which is going to display Z2. Okay, Z2 is going to be displayed as 1.1 comma 2 in parentheses. The second value is just displayed as 2 because the point 0 is 0 and we don't display trailing zeros. When we display star PZ, that's going to display 5.7 comma minus 2.7. And when we display ZA sub 0, that's going to be minus 3.1. Now this is a typo, actually. That should be a 2.2. Okay, there is a 2.2 in the imaginary part of ZA sub 0. Okay, well, fortunately for us, we don't actually have to define this complex type ourselves. The standard C++ library already provides a complex data type. You can take a look at the documentation for the header complex, which describes the data type and all of the facilities that are available. Let's look next at a structure where the components are not all the same. This is our employee structure in which each employee object has an ID, which is an integer. Each employee has a name, which is an array of 10 chars, and each employee has an hourly rate, which is a double. We're going to have a putemp function that receives an employee object by value and displays the name, the ID number, and the rate with a little bit of beautification. So we're going to get name colon space and the name, and then comma ID colon space and the ID, and comma rate colon and the rate. Here is a really trivial program. We're creating one employee object, John, with the ID number 123, name John, rate 60.5, and then we're going to do a putemp of John, and that's the end of the program. But instead of having just one employee, let's suppose that we have our employee structure definition and our putemp function defined, but our main function is going to create a company in which we have space to hire 10 employee objects. Although for the moment we're only initializing 3 of those objects. Here, company is an array of 10 employee, and the first 3 are initialized with 1 UFAN 57.5. My apologies if I'm butchering these names. These are former students. Another employee is ID number 2, fan, and rate is 62.0. And then ID number 3, yipping, and 58.25. Now, since company is an array of 10 employee objects, all 10 of those employee objects will be allocated in memory, and the trailing ones that were not specifically initialized will become initialized with zeros by default. Let me jump ahead to a diagram of this array. All right, here on slide 16, we have a diagram of that array as it's laid out in memory and initialized. So company is an array of 10 structures. Each one of these structures has 4 bytes for the ID, an integer, 10 bytes for the name, which is an array of 10 chars, and then 8 bytes for the rate, which is a double. Depending on your processor, there may or may not be some unused padding bytes between the integer and the character array, or between the end of the character array and the rate. But if your system is using a modern Intel processor, there won't be any padding. That's just going to be contiguous memory all the way across for each one of those structures. Then we know that for an array elements are always contiguous ascending. And so if the structure itself is contiguous, then subsequent structures in the array are also going to be contiguous and in ascending memory locations. We filled in zeros for the values of all of the ints and chars and doubles of the uninitialized 7 slots in the array. Well, now that we've got our company, we may want to have a loop that displays the people in the company. The default ID, if we don't initialize, is 0. So let us do a test. Our for loop is going with an index from 0 up to 1 less than 10. So from 0 to 9, we get a total of 10 employees that we're going to test. And we only want to display information about an employee if the employee has a non-zero ID. All right, so the first time through, company sub 0.id is going to be 1. And we do want to display the information about this employee, company sub 0. Then we'll increment our counter. The counter is still less than 10. Company sub 1.id is a 2, which is non-zero, so we'll display information about the second employee and go back and display information about the third employee, and that's it. We will not display information about any more employees because as we go through the trailing 7, we'll discover for each one that the employee ID number is 0. And so the if condition fails and we don't print out those employees who have 0 ID, no name, 0 rate. Okay, so using an integer subscript and using company sub I to access an individual employee within the company is one common approach to iterating through the elements in an array. But another approach that's almost equally common is to use a pointer to step through and point to the successive items within an array. Here we're declaring P as a pointer to an employee. P is uninitialized, so at the moment, P is just pointing off into some random location in memory. And if we made an attempt to use P, for example, if we said star P.rate gets some value, well, that would jam the floating point representation of 77.7 into some random location in memory, which might very well cause our program to crash, or we might just accidentally get away with it. It's better always to initialize an object, as I've said before. So more often, if we did a creation of this pointer P, we would initialize it to 0 or to the special token null pointer, depending on what generation of compiler we have. Now, it turns out that these values, 0 and null pointer, are entirely interchangeable. My guess is in real code that you're going to see a lot more zeros representing null pointers than this string null pointer that was introduced with C++11. So what we're going to use P for, our pointer to employee, is to point at the successive employee elements within the company array. We can initialize or set the initial value of P to company. Remember that the name of the array, company is simply the shorthand for the address of company sub 0. So when we do that, P is going to be pointing at the first element within that array. By the way, in the diagram, I've intentionally indicated that company itself I can think of as being like a fixed pointer pointing at the initial element of the array. I have not drawn a box around this arrow because company is not a pointer object whose value can be changed. Company is like a fixed pointer that's always pointing to company sub 0. All right, now where is the end of our array? The end of our array, in a for loop, we actually always want the end to be one past the actual final element of the array. So we would like our end pointer to point down here, just below the array. How can we get the number of employees in the company? Well, in the first part of this program, we sort of cheated a little bit. We said that company was an array of 10 employees, and then we just used the 10 here in our loop without commenting on it or making a big deal out of it. But what we're doing here on slide 14 is we're making the mistake of using what are called magic numbers. If some other programmer looking at your program sees the 10 here and then sees the 10 here, very likely they're going to understand that those are supposed to be the same numbers as each other. But on the other hand, maybe not. And if somebody else comes along to do maintenance on this program later, as our company gets bigger, they might change the actual size of the company array to, let's say, 50, but they will very likely not notice the 10 down here and forget to change that to a 50 as well. And now we've got a mysterious bug in our program. So we would like really to specify the size of the array in just one place. And then anytime we need that value, we can figure it out on the fly by using this trick. If you ask for the size of an array, what you will get back is the total number of bytes within the entire array. If you divide that by the size of the first element in the array, that is the number of bytes in the first element, the total size of the array divided by the bytes per element is going to be the number of elements. So we can figure out on the fly that there are 10 employees in our array by doing this size of company divided by size of company sub 0 computation. And that will always work no matter whether company remains at 10 employees or if somebody increases that to 50 or 1,000 or 10,000. This computation will be able to figure out what the maximum number of employees is in my current array. Okay, so to mark the end of the array, what I want to do is take the start of the array and add the number of elements that there are in the array. Company plus 10 in this case. Well, let's see. Company points to the first slot, the sub 0 slot. Company plus 1 points to the sub 1 slot. Company plus 2 points to the sub 2 slot. Company sub 9, or company plus 9, pardon me, points to the last slot. Therefore, company plus 10 is going to point one past the last slot. Okay, so we've got CEnd set up, and let me swap screens now. I want to move my code over to the left so that I can draw on my diagrams on the right-hand side. Okay, so I've shifted my code to the left, and I've put up my diagram here on the right. CEnd has been set to company plus 10. So CEnd is actually pointing at this employee object that is one beyond the end of the allocated array. Then when I say P gets company, that's going to cause P to point to company sub 0. So now we have this situation. And in our for loop, we're saying while, or the test is P less than Cend? Certainly P is less than Cend, because recall for an array that these are in ascending memory locations. So because P is less than Cend, we're going to evaluate P arrow ID. All right, P arrow ID is the 1, the ID field in the first slot here, the sub-zero slot of company. And so we will print out with putemp star P. That is, we're going to display this whole company sub-zero value using putemp. And I've added a C out here to put a new line on the end of that. When I increment P in the change expression, how many bytes forward in memory does P get moved? Aha, well, we don't have to know. We can think about our declaration, and we can say, well, let's see. We've got 4 for the int, we've got 10 for the array, we've got 8 for the double, so that, let's see, 4, 8, 12, 22. So P should move forward by 22 bytes. Well, we don't have to figure that out. The compiler automatically knows, and so the compiler is going to automatically bump P forward by 1 employee's worth of bytes. So P now points at the second slot, the sub-1 slot in the array. P is still less than Cend. Okay, here's our situation now. P is still less than Cend. So we'll display information about the second employee and bump to the next one. And that's just going to iterate. We start pointing at the sub-0 slot, then the sub-1 slot, then the sub-2 slot. Once we get past the sub-2 slot, P arrow ID is going to then be 0 all the way to the end. And when we get down here to where P is equal to Cend, the loop will terminate and my whole program is over. Let's look at and run this program just to make sure that it works. Here is the program. It's called company.cpp. Here's the structure and the putemp function. The top half of main, in which we declare the array and then use the integer subscripts to go through and access the elements of the array. And then in the second half of main, we are declaring our pointer variable P, and we're computing the number of elements in the array, setting the end pointer to point one past the end of the array, one past the last item within the array, and then our for loop using this pointer to step through the array elements. If I compile this, and run it, we do see the 3 initialized employees displayed first with the loop that was using the integer subscripts, and then again in the loop that was using the pointer variable to point at the successive slots. I want to be clear that it's perfectly fine to use a for loop with an integer subscript to access the elements of an array, but it's also perfectly fine and equally common to use a pointer to step through and point at the successive elements in an array. And you'll see both of these styles used in real code. You have to be able to read both of them, whichever one you decide you prefer to write. Here on slide 17, we summarize the notational algebra that you really have to know. Generally, good programmers will use a consistent style of notation. However, one good programmer may use a different consistent style from another good programmer. The case of array subscripts versus using a pointer to step through an array is just one example. Bad programmers will use whatever notation pops into their head, and they may write notation that really just looks pretty terrible. And it may not be consistent at all. So you really need to be able to read almost anything that gets thrown in front of you. Let's suppose that T is the data type of some structure, and within that structure we have some member named mem. Then if we have an array of T called A, and if P is a pointer to T, this expression, P gets A, means that P is going to contain the address of the initial element within the array A. That is, P gets A is equivalent to P gets address of A sub 0. Now, P is pointing at a T object, so star of P in parentheses dot mem accesses the mem component of that structure that P is pointing to. This, as we know, is equivalent to P arrow mem, but it's also equivalent, remember that star P, when we're dealing with arrays, is equivalent to P sub 0. So star P in parentheses dot mem is also equivalent to P sub 0 dot mem, and some people prefer to write it that way. A sub n, where n is an integer, is the sub nth element within the array A. A sub n dot mem is the dot mem member of that particular structure within the array A. And remembering our A sub n equivalence, A sub n is equivalent to star of the quantity A plus n. And if we put all that mess in parentheses and put dot mem after it, that's an alternate way of getting to that particular member of that structure. We can replace the star and the dot with an arrow. So A plus n arrow mem is yet another alternative. A itself, of course, just stands for the address of A sub 0. So the address of A sub 0 plus n, all in parentheses, arrow mem, is yet another way of accessing a particular member of a particular structure in an array of structures. Okay, so some of these are sensible, some of these are sort of crazy, some of these would be written by someone who's not too sure of their abilities as a C++ programmer, but they all mean the same thing. Let's try some practice with this. You'll notice that there are some blank slides in your notes for taking notes if you wish. For example, how could we access this employee object within the company array given either company or P or C end as a starting point? Now actually I want to put my diagram over on the left so that I can show you the notation on the right. So I'm going to do that. Okay, so I've shifted my diagram over to the left, and I've fired up a VI editor in my Ubuntu window on the right so that we can try various notations. So company, let's recall, looks like so. Employee company sub 10. All right, so company is an array of 10 employees, and we actually had initialized that. I won't fill in the initialization all over again. P is a pointer to an employee, which we didn't initialize, but this time let's initialize P to company plus 2, all right? So P is pointing at the sub 2 item of the company array, and C end is company plus, well, the number of elements in company is, well, all right, I'm going to cheat. I'm just going to say 10, but we could have said size of company over size of company sub 0, all right? I do, unfortunately, have an equal sign missing between C end and company. So rather than redoing all of these slides, just realize that there should be an equal sign in there. So how do we get at that green outlined employee object? Well, one way is that that's company sub 1. Equivalently, it is also P sub minus 1, because I can treat a pointer as an array, and that green outlined employee is one prior to where P is pointing. Of course, I can use my star and my offset with plus, so I can say star of company plus 1 or star of P minus 1. I can say C end sub minus 8, I guess it would be. Have I counted right? So C end sub 0 is the element 1 past the end. Sub minus 1, 2, 3, 4, 5, 6, 7, 8. It's minus 9. All right, so not quite. So C end sub minus 9. All right, so I can do lots of devious trickery in order to access that green outlined employee item within the company array. Next, let's take a look at how we can access this green outlined element, member, I should say, of this particular element here in the company array. Okay, so let me delete these things here. All right, so we can say company sub 4 to access that entire employee object. Company sub 0 is the first element, 1, 2, 3. So company sub 4 is this entire element of the company array. And then dot rate is how I can access the rate component. Or I can say star of company plus 4 dot rate. Or I can say company plus 4 arrow rate. Those are all equivalent notations, and then I can do similar gymnastics with P and with C end. What if I needed the address of that thing for some reason? Well, to get the address of that thing, I can simply stick an ampersand in front of each of these. So this gives me the address of the rate member of company sub 4, or the address of the rate member of star of company plus 4, or the address of company plus 4 arrow rate. So there's how I get the address of that particular member. Next up, let's talk about the ID field here. Okay, well, let's see. So that's company sub 2 dot ID, easy enough, or P arrow ID, right? Since P is pointing directly at that element, P arrow ID is correct. Or star of P in parentheses dot ID is the ugly way to say the same thing. Or P sub 0 dot ID works. Company plus 2 arrow ID works. And I can do similar things starting from C end. All right, let's take a look at one more. How do I access this F in the third position in the name array of the first element in the company? Well, let's see. So the obvious way, I guess, is company sub 0 dot name sub 2. All right, so company sub 0 dot name sub 2 gives me that F. This is also company arrow name sub 2, which is in turn star of company dot name sub 2. I have an extra layer. Yeah, no, I'm good. Yeah, no, I don't need these parentheses. I got an extra layer of parentheses in here that I don't want. Oh, and we can even go crazy and say star company dot name plus 2 star of all that business. Okay, so star of company dot name is the address of the capital Y, plus 2 is the address of the little f, so star of all that is the little f. All right, you get the idea. We can go berserk with different notations for this. Some people do it one way, some people will do it another way. Some strange or ignorant people will do it in some bizarre mixture of ways. You will also occasionally run something called a code generator that might do something like converting Python code into C++ or Java code into C++. And these programs that do code conversion will often do quite nasty nested star arrow dot notation that with any luck you won't have to read, but if you discover that there's a bug in these code conversion systems, then you might find yourself having to wade through some truly bizarre looking code to see if you can figure out where the bugs are. All right, so that takes care of structures as well as arrays of structures and pointers to structures and the relationships among all these things. Now, the very last thing that I want to mention here is that a struct is the foundation for the class concept in C++. A class is sort of like a struct, except that a class has both data members as well as member functions that operate on the data. So we'll be getting to that in a couple of more lectures. A struct we generally use when all we need is just a bag of data. It's sort of like an array, except that the elements within the members within a structure can be of different data types, whereas the elements within an array are of the same data type.